You've probably heard on TV and social media the term heat dome, but nobody has really explained what it is. It sounds dramatic, like a glass lid dropped over half the country. But here's the part that's rarely explained. The dome is not just hot air sitting at the ground. The dome is the actual shape of the atmosphere above you during a heat wave. And once you see that shape, heat waves stop looking random. They start looking like Mother Nature's hidden architecture. A heat wave is the impact of a heat dome. Several days of abnormally hot weather, sometimes with brutal humidity and nights that never cool down. A heat dome is one of the patterns that can create it. A large, stubborn ridge of high pressure aloft that traps, compresses, and recycles the heat. Let's build it up from the ground up. In this diagram, imagine two columns of air side by side. A cooler column and a hotter column. Warm air is less dense, and just like anything that warms up, it expands and takes up more space. So the hot column expands upward because air can't go down into the ground. Meteorologists don't only look at height in feet. We look at pressure levels, with pressure measured in millibars, 850 millibars, 700 millibars, 500 millibars, 300 millibars, because pressure decreases as you go up. Roughly speaking, 850 millibars is around 5,000 feet, 700 millibars around 10,000 feet, 500 millibars around 18,000 feet, and 300 millibars around 30,000 feet. But these levels are not flat. In warm air, those pressure surfaces are higher because the hotter column of air takes up more space. In cold air, they're lower, relatively speaking. So when a warm column sits next to a cold column, the upper atmosphere actually tilts down toward the cooler side. That tilt matters because air responds to pressure differences. The pressure gradient force tries to push air from higher pressure toward lower pressure, but on a rotating Earth, the Coriolis effect turns moving air to the right in the northern hemisphere, as you saw in this video. When those two forces balance, the wind flows roughly parallel to the lines of constant height along a pressure level. That's the geostrophic wind. For more on the geostrophic wind, check out this video right here. Now, here's the key. Because warm air expands the column, the height difference between warm and cold air gets larger as you go upward. The slope gets steeper. A steeper slope means a stronger pressure gradient force and a stronger geostrophic wind. In plain English, the bigger the temperature contrast between air masses, the stronger the winds become the higher you go. Stack that over thousands of miles and you get the jet stream, a fast river of air near the cruising altitude of jet aircraft, born from the battle between warm tropical air and cool polar air. Now look at a weather map. When the jet stream bends south, that's a trough. Cooler, stormier, unsettled air. When it bulges north, that's a ridge. Warmer air, higher pressure aloft, and often quieter weather. But on a flat map, a ridge just looks like a bend in the jet stream. But in 3 dimensions, that ridge is actually a dome. The pressure surfaces arch upward. Air inside the ridge slowly sinks. As it sinks, it compresses and warms. That sinking air also acts like a cap, making it harder for clouds and thunderstorms to form. Fewer clouds mean more sun hitting the ground. More sun means more heating of the ground, and if the ground is already dry, even less energy goes into evaporation. More goes straight into heating the air, and the more the air heats, the bigger the heat dome becomes. That is how a heat wave can become self-reinforcing, getting hotter and hotter. A bad heat wave is not just about the air temperature, it's the combination of high afternoon temperatures, high humidity, warm nights, stagnant air, urban heat, dry soils, and duration. The body can fight heat for a while, but it needs recovery time. When overnight temperatures stay in the 70s or 80s, the danger compounds because people, buildings, roads, and power grids never really reset. This is why heat risk maps light up when the atmosphere lines up the wrong way. It's not only the number on the thermometer, it's the duration, the humidity, the nighttime lows, and who is exposed without reliable cooling. And heat risk is greatest for places that aren't used to this heat. So why do some heat domes last so long? Sometimes the jet stream locks into a blocking pattern. One classic version is called an omega block because the upper level flow resembles the Greek letter omega. A big ridge gets pinned between troughs, and instead of sliding east like normal weather, the pattern stalls. Under the ridge, the same feedback loop keeps running. Sinking air warms, clouds are suppressed, sunshine bakes the surface, dry ground heats faster, and the expanded warm column helps maintain the bulge in the pressure level aloft. Around the edges, thunderstorms may ride, the ring of fire, but the core of the dome stays capped and hot. But heat domes do end. They break when the jet stream finally shifts. A trough eventually digs in, and a cold front undercuts the heat. Thunderstorm complexes punch into the ridge. Clouds and rain return. Soil moisture increases. The high pressure ridge weakens, flattens, or relocates, and the dome opens. So the next time you hear heat dome, don't picture a cartoonish lid over your town. Picture a massive, 3D ridge in the jet stream, a bulging column of hot air, and a feedback machine that can turn a few hot days into a dangerous event. Weather is not just what happens at the surface where we humans live. It is the whole atmosphere stacked above us, moving like an ocean we live underneath. If you want the science behind the forecast without the hype, subscribe to Untamed Skies, where we follow the weather from the map to the sky to the people living under it. Keep looking up.